historias, orgullo, pasión, memoria, trascendencia, prendidos en el alma.
Universitas, un corazón que abraza su historia y su futuro.
Somos grandes historias, orgullo, pasión, memoria, trascendencia, prendidos en el alma.
Universitas, un corazón que abraza su historia y su futuro.
Somos universitas, la voz de nuestras generaciones. Somos universitas, servicio, amor y libertad. Universitas, somos grandes historias.
Good morning, everyone, and welcome. I am Jocelyn Paredes, and on behalf of the Department of Industrial and Environmental Engineering and the San Pablo Catholic University, we are delighted to welcome you to the International Environmental Conversation about technological innovation and strategies in the availability and sustainable management of water and sanitation, related to SDG number 6. This year, the activities of the university, called Universitas, are mainly oriented to the university community and to Arequipa, around these 25 years of the university. So we are celebrating, and we thank all the people who are connected now through the Zoom and also through the Facebook platform. Right now, I would like to invite the director of the School of Environmental Engineering. So please, Magister Joel Arias, could you please give us some words on behalf of the Department of Industrial and Environmental Engineering, and also please give us the honor to open this event.
Good morning, everyone. Thank you very much, Jocelyn, for the introduction. I don't know if you can hear me.
Yes, we can hear perfectly.
Thank you very much. Well, I just want to say thank you for to all the participants that are joining us today for this activity. For us, it's a pleasure to have the participation also for the specialists from every part around the world. Thank you very much, Dr. Achal. Thank you very much, Dr. Selena, and thank you very much, Dr. Kostel, for joining us today in this event related to the topic of water. We know that we have many problems around the world, also in our country, related to the management of the water and also the sanitation services. So now have the opportunity to share with you your experiences with the students and all the community related to the topic is going to be very, very important for us. This activity is part of the celebration that we have this week, which is called Universitas. So we hope that you can enjoy this activity. Thank you very much for the participation, and I hope that you can see me again in any other activity. Thank you very much.
Thank you, Joel, for this welcoming and also for this opening of the event. And now, are you ready to begin? Well, the sustainable management of water and sanitation is a topic of great importance, and this event seeks to understand the problems surrounding the gaps in access to drinking water and basic sanitation services. And also we are going to learn about innovative wastewater treatment technologies that are being applied and doing research on the field. So it is moment to invite to our first specialist. So our first speaker is PhD Kostel Bumbak, who is joining us today. Kostel is a senior research scientist leading the biotechnology research team within the Environmental Technology and Technology Transfer Department of ECOIN in Romania. He has 17 years of experience in research projects focused on development and optimization of biological wastewater drinking water treatment technologies, also biodegradability studies, soil bioremediation, and waste to fuels technologies. Specific achievements in the field of environmental biotechnologies are, for example, 5 patents, 4 pending patents application, more than 70 scientific papers, more than 30 projects involved. For these 9 are he was project manager, including European funded projects under Horizon 2020. Also, he has a sound experience in both lab scale development and also pilot scale demonstration of water treatment and sanitation technology. Right now, it is my pleasure to invite Dr. Kostel Bumbak to join us and share with us your presentation. Thank you for your presence today, Kostel. You're very welcome. Let's begin with you. Kostel, we cannot hear you.
Can you hear me now? I changed the mic.
Yes, perfectly.
Okay. Thank you very much for the invitation and for your nice introduction. I will start sharing my screen. Can you enable screen sharing for participants?
Sorry, por favor, el equipo de organización, ¿podrían activar la opción de compartir presentación? Just a moment, Kostel. They're going to activate the sharing options.
Okay. Let's put it in slideshow mode. Not sure why my screen sharing was paused. I think we're ready now. Sorry for this small delay. Can you hear me?
Yes, we can hear you, Kostel, and the presentation can be seen now. So we are delighted to have you here. Please begin. Thank you very much, Steve.
So, as Jocelyn said, I'm a senior research scientist within the Environmental Technology and Technology Transfer Department of ECOIND Romania. And I'm also founding member of Novaqua Alliance, which is based in France. I will give you a short introduction on SDG 6 and some history of sanitation. And afterwards, I will give you a few examples of the technologies we have been developing in the last years. So, ensuring water and sanitation for all by 2030 is an ambitious, sustainable goal of the United Nations. However, ensuring universal and safe and affordable drinking water involves reaching almost 800 million people who lack basic services and improving accessibility and safety of services for over 2 billion. For example, in 2017, worldwide, there were 4.2 billion people who lacked safely managed sanitation services, and 2.3 billion lacked even basic sanitation, while 673 million people are still practicing open defecation. While substantial progress has been made in increasing access to clean drinking water and sanitation, billions of people, mostly in rural areas, still lack these basic services. Given these numbers and huge discrepancies between developed and underdeveloped countries or urban and rural areas of some countries, in terms of access to safe drinking water and proper sanitation, the goal of ensuring water and sanitation for all is rather a common sense objective aiming to decrease the health impact of water diseases and ensure basic quality of life, as water is indeed a common good regarded as a heritage which must be protected, defended, and treated as such. We cannot talk about innovation and future management strategies without taking a glance at the history and overall progress so far in the field. Thus, the early evidence of sanitation in antiquity, almost 4,000 years ago, under the pressure of urbanization and increased population density area of Knossos in Crete, driven only by the need of waste management, they developed an elaborate system of drains, conduits, and pipes to provide water and sanitation for the Minoan Palace. The Roman did build many structures dedicated to improving sanitation. In addition to public toilets, they had bathhouses and sewer systems like the giant Cloaca Maxima in Rome, which was one of the first sewage systems in the world. Almost every city in the ancient Rome had large public latrines, which were, for many people, often 20 or more. Although the commodes were functioning, they were still gross by today's standards. Besides the driving force of waste management need, under the pressure of urbanization and health impact, the Romans added legislative constraints in the year of 500 BC towards proper waste disposal, meaning more clearly that the Dejecti Effusive Act was against throwing feces and other objects like wastes in the street. However, this rule was only applicable during the day. More recent innovation involved the dry earth commode from 869, which was mainly a bucket under a seat with some sieved earth as a smell blocker. And there are also water toilets, which have been previously developed in the antiquity, and later inventions. I will insist only on the valveless waste preventer type toilet with a siphon, which is largely used nowadays, that has been developed by Thomas Crapper in 1880s. The invention had a major impact as the inventor's name itself has been adopted as a verb to take a crap as a synonym for defecating. Current state of development involves sewage systems are still being built both as combined sewer systems and as separate sewage systems. When separate sewer lines are being constructed, dedicated rainwater storage and treatment facilities are being built, often with the aim of water reuse. Vacuum sewage are less common than gravity systems, but are still adopted, especially on sites with flat areas and with sandy soils, or with high ground water table. Decentralized sanitation and reuse, also known as DSAR, driven by the principle that concentrated wastes are relatively easy to manage, while diluted wastes are of centralized systems require large investments for collection and treatment. And also eco-san sanitation systems offer a new philosophy of dealing with what is presently regarded as waste and wastewater. Ecosan is based on the systematic implementation of reuse and recycling of nutrients and water as a hygienically safe, closed loop and holistic alternative to conventional sanitation solutions. Ecosan solution systems enable the recovery of nutrients from human feces and urine for the benefit of agriculture. In terms of wastewater treatment, the ambitions gradually increased, driven by the combined pressures of environmental protection, awareness of health impact due to improper sanitation, and population increase. Thus, the treatment of wastewater developed from simple mechanical treatment with grit removal or screening to chemical treatment for waste stabilization, biological treatment for organic load removal, sludge treatment and resources recovery, advanced phosphorus removal, either through biological uptake, either through chemical precipitation, advanced nitrogen removal processes such as Anamox, Holland, or Canon, processes as alternatives to improve and optimize conventional biological nitrogen removal. Disinfection is being adopted broadly as standards in developed countries. And in terms of micropollutants, fate and occurrence of micropollutants in wastewater treatment plant is currently being investigated as researchers are gathering more information on their environmental impact. So different approaches are possible. It should become clear that the choice for the collection and transport system would determine for an important part the subsegment treatment and reuse, while the type of use or disposal will determine the extent of treatment. And the type of reuse will determine the extent of advanced post-treatment, especially in terms of pathogen removal. For the time being, the state of the art shows us that along with the tightening of the legal norms for wastewater discharge and implicitly for the treatment needs, the degree of complexity of the operations to which the wastewater is subjected has increased from a simple mechanical treatment, screens, descenders, to secondary treatment, tertiary treatment, or membrane biological treatment. These treatment requirements increase, implicitly impacts on energy consumption and treatment costs. For example, from a technological point of view, large treatment plants, at least in Europe, can be found or tend towards this technological stage. This is the representation of a classical biological treatment with activated sludge in anaerobic, anoxic, and aerobic condition, meaning that this is the advanced nutrient removal process. Provided with dedicated sludge lines, with residual sludge thickening, anaerobic digestion, and cogeneration for biogas for power generation. In the quest to reduce energy requirements for wastewater treatment and respect at the same time the increasing treatment standards, the research trends are focusing on different alternatives. And some of these alternatives include optimization of wastewater treatment processes in order to increase treatment efficiency, increase treatment capacity in the same reactor design to adapt the population growth, or decrease investment, operation, and maintenance cost of newly built systems by adopting innovative technologies such as aerobic granular sludge technology. Another approach would be to reconsider the activated sludge system and focus also on biological models to work in synergy with bacteria like microalgae, earthworms, or other biological models. Last approach, and probably most appropriate to help us reach the goal of sanitation for all, would be to shift from highly engineered systems to low-cost, nature-based solutions, easy to install and low maintenance. There is a great need for decentralized wastewater treatment systems, especially in the global south. The cities are growing at such a rate that the conventional way of providing sanitation and water is not going to work, as we cannot put that infrastructure in fast enough. An example for wastewater treatment optimization as an alternative can be the aerobic granular sludge technology, which can be accommodated in existing sequential biological reactors to increase treatment efficiency, or the treatment capacity in newly built centralized wastewater treatment systems, as it offers the possibility of lower investment, operational and maintenance costs. The advantages of the aerobic granular system derive from the biomass itself, as it represents a specific case of biofilm meaning that the bacteria are adhering to themselves in granular shape structures with increased settling ability and specific structure that allows the accommodation of different environmental conditions in a single reactor, because the nutrients and oxygen are diffusing towards the center of the granules. Thus, the granules have an anaerobic core, an anoxic middle layer, and an aerobic shell that are able to accommodate simultaneous nitrification, denitrification, and phosphorus removal. Moreover, the system has a lower residual sludge production and no need for a thickener, making sludge management even easier. Another alternative would be the granular microalgae bacteria system, which is currently under development in our department. And there are some other research groups which are focusing on this technology or similar technologies to this one. One is in the United States, one in France, and one in the Netherlands. These are some of the groups we know. This technology is focusing on taking advantage of sunlight and natural photosynthesis of microalgae in an induced symbiotic system with microalgae and bacteria. Thus, the microalgae are producing the oxygen through photosynthesis and are using carbon dioxide resulted from bacterial oxidation of organic matter, while the bacteria are using the oxygen produced by the microalgae for nitrification and organic matter removal and produce CO2 to sustain the growth of microalgae. Moreover, the microalgae are used for their enhanced capacity of reducing nitrogen and phosphorus content to very low limits in treated effluents. The innovation of ground recovery technology, as we call it, lies in the specific operational conditions used to achieve the granulation state of biomass, making economically feasible the separation process, settling speed of the microalgae granules are similar to that of aerobic granular sludge, meaning above 20 meters per hour, and overcome the main disadvantage of microalgae technology. The treatment performances of the system meet the highest standard for discharge, and the technology itself is currently at lab scale, but will be soon scaled up and demonstrated in real environmental conditions within the ground recovery project. As an example of low-cost nature-based solution, I will present the Inocua System developed within the Inocua project for decentralized municipal wastewater treatment. The Inocua System is modular by design. The main idea is to add different modules representing complementary technologies according to treatment requirements and reuse perspectives, thus trying to meet the discharge limits of any country, making the system versatile and adaptable to local requirements of both rural and urban environments. Available technologies for the treatment train are lambifiltration, also known as vermifiltration, which relies on the power of earthworms in an engineered trickling filter to treat wastewater. The module being responsible for primary and secondary treatment, TSS and organic load removal, but also nitrification and partial denitrification have been identified with consistency in our demo sites. Daphne Filtration, the second technology, is used as a polishing step or tertiary treatment based on the power of Daphnias, also known as water fleas, to further remove fine suspended solids, including bacteria, while the biofilm on the interior baffles of the reactor are responsible for further nutrient removal to a certain extent. The third technology is the biosolar purification, also used within this treatment train as a polishing step. This is based on a thin layer cascade photobioreactor, responsible for advanced nutrient removal through the activity of microalgae biofilm. The fourth and final technology of the treatment train, which can be accommodated in the Inocua system, is the UV disinfection unit, which is based on a LED UV source in a quartz sleeve reactor designed for specific disinfection application, especially when water is being reused. Based on the research data gathered during prototyping phase of the Inocua project, the pilots were installed in Ireland and Spain. During the demonstration phase, 11 demo sites have been installed across 10 countries to demonstrate in real environmental and operational condition the long-term viability of the technology. Different integration of the Inocua technologies have been chosen depending on influent type and quality, treatment target, discharge, or reuse option, considering the climatic condition and space availability. In all demo sites, the main treatment is being performed within the Lambri filter, the core technology of the Inocua system. While as polishing steps, we have tried either Daphne Filtration or biosolar purification, or even both in parallel lines for comparison reason. Where reuse of the treated effluent was intended, the UV disinfection module was added for safety reason. Now, some results from a few of the demonstration sites. The pilot site in Ireland has been operated for more than 2 years in real environmental conditions at Tuam Research Facility of National University of Ireland in Galway. The specific testing conditions included temperatures of 5 to 20 degrees Celsius for the influent wastewater, while ambient temperature were from -5 to 26 degrees. The Lambri filter had an active layer of 1 meter in height and was operated at a specific hydraulic loading rate of 0.5 cubic meter per square meter per day. The site was used as pilot site as well to assess loading rates influence, unexpected shutdown impact, different influent delivery mechanism, and so on. The removal performances registered were about 80% for TSS and COD, and approximately 90% for BOD5 and nitrogen removal. During testing, no maintenance was required, except the need to top up with wood chips to maintain the height of the active layer. Another demonstration site is this one in Italy. In Italy, we have installed an example of compact Inocua system in the basement of a residential house, treating the wastewater generated by 4 people. The configuration installed is Lambri filtration for main treatment and UV light disinfection system as a requirement to meet the microbial load limits of local discharge regulation into the sea. The treatment performances have been consistent for almost 2 years now, meeting at most times the discharge limits. The system installed in India and Peru are evaluating comparatively the performances of the Lambri filter in combination with Daphne filtration or biosolar purification as polishing steps. First, the wastewater is being treated by the Lambri filter, and afterwards the flow is divided. One stream directly goes to the Daphne filter following the UV system, while the other goes directly to the biosolar purification system. The Inocua system in India is treating the wastewater from 9 households from a rural low-income community next to Bangalore. The influent is of high strength, typical to a low flushing community, as the water consumption is approximately 20 liters per person per day due to water scarcity, which is a major issue in India. The influent fed to the Inocua system had about 2,200 milligrams per liter of TSS, more than 1 gram per liter of BOD, approximately 100 milligrams per liter of nitrogen ammonia, and the temperature ranging from 20 to 38 degrees Celsius. Even in these harsh testing conditions, The system performed really well, achieving removal performances above 80% for most quality parameters tested, only through Lambri filtration alone. Adding supplementary modules as polishing step improves the quality of effluent, reaching at most times removal performances above 90%, both in with the Daphne filtration or biosolar purification. Thank you very much for your attention. If you have time and you're curious, you are invited to see on the website of Novaco Alliance some of the projects we had for the Inocua project. If you have any questions.
Yes, Costa, we will have questions at the end of this event.
Okay.
So please stay with us.
I'll be here.
That was an amazing presentation. And also that was an amazing way to start the event. Thank you so much, Costa, for sharing this important knowledge with us. And quick fact, Costa was here in Peru a couple of years ago, installing the first biological wastewater treatment pilot plant as part of the demonstration component of the Inocua project. And together with the guidance and support of all our international partners, we managed to give Arequipa a new and innovative alternative for wastewater treatment. So again, thank you so much, Costa, for sharing then and now all your knowledge and expertise with us. Now, are you ready to our second presentation? I am glad to welcome PhD Ashal Gar. He's postdoctoral in environmental science. He worked as a research and innovation manager with the Department of Wastewater Management of the city of Cincinnati, Ohio in USA for 20 years. He also received a Fulbright Fellowship in 2012 for teaching and research at Namibia University of Science and Technology in Africa. He also received a second Fulbright Fellowship in 2020 to work at National University of the Altiplano, Universidad Nacional del Altiplano in Puno, Peru. He is also a professor at the Miami University, Oxford, in Ohio since 2014, and he serves as a director on the board at Chemists Without Borders, an international non-profit humanitarian organization. So please let me welcome Dr. Ashal. For the next 20 minutes, he will share with us his experience. Thank you very much, Ashal, for being with us today, and let's begin with you now.
Thank you very much for the introduction. Can everybody hear me and see the slides?
Yeah, the slides not yet, but we can hear you and see your camera also.
Okay, so why don't you see the slides? Then let me try one more time. So I'm sharing my screen. Here it is.
Not yet.
Okay. Can you see now?
Okay, now it's yes, now it's sharing. Great, Ashal, let's go with you.
Okay. So do you see the full screen or everything looks okay?
Not the full screen, it's just the PPT.
Let me try one more time. I think something is okay. How about now?
Yes, that's perfect.
Very good. So give me one more second and then, okay. Thank you again very much for inviting me. And you just heard Dr. Kostel Bombak, a very beautiful introduction, a historical introduction about the wastewater and sanitation, going back to the movements. That was a wonderful introduction. Now I'm going to take you follow on that and build my slides. Although we never spoke, but I seem like presenters were put in a way that starting from the historical perspective and going forward. So I'm going to talk a little bit about the current status, how the wastewater is treated currently in most of the big plants, and then where we are leading in the future. And that's where I will take you now. So let's go, and this is my slide. So Okay, so what I have done for the to help the people, I know when I was in Peru 2 years ago, and I realized that most students did not speak English. So I tried to make some slides in Spanish. So to just help them from what I'm talking, although I will be talking in English, but slides will be in Spanish. So just to get some idea what we are talking here. So the wastewater treatment in general, there are 3 steps when we receive wastewater from the homes, industries, and other sources. When it reaches to the wastewater treatment plant, there are 3 things happen. First is the primary treatment, and then the secondary treatment, and finally, before the wastewater is, or what we call effluent, the final effluent, is released to the river or any other environmental source, then we disinfect it to kill all the bacteria and viruses, so we don't pollute the receiving water body. So these are 3 steps which are part of this treatment. So here this I'm just going to give a little bit more background information about each step of the treatment. So in the collection, we get the water from homes, industries, that's the first part, and water comes from the collection site and goes from here. This is the raw sewage. And then it goes through the screens, which are big, large screens, to remove all the big objects like bottles, papers, any kind of big items, the rocks, they are removed at this step. And then only the water and organic waste moves forward and goes through this process. And then next step is to remove the smaller objects, like heavy objects like the rocks and sand. They are, so the water goes in a big tank, and that's where all the sand and rocks, they are settled on the bottom, and then they're removed. So what we have in the here is the dirty wastewater with all the feces and organic matter. So that is the first step here. Then it moves to the next step where we call primary clarifier. In this step, is again very big, large tanks, very deep. Sometimes they're 20, 30 feet deep. And then we remove most of the solids. These solids are remaining sand particles, and also majority of them are organic matter, like human waste, feces, and so on. So they are removed at this step. And this solid on the bottom is called primary sludge. And the water on the top is much cleaner now because we have removed most of the solids here. Then it moves to the next step, and that is called, this is the, well, this is the, I'm sorry, this is the screen I was going to show this step. These are the screens, like they look like this one. So, and then water moves to the next step, secondary treatment. So water coming from the primary clarifier goes to the large tanks, which are aeration tank. Here we have the air compressor and the pumps, which are pumping the air in the tank and mixing with the water and with the air. So bacteria has a lot of air and the oxygen to eat or the digest or break down all those organic matter in the sludge, in the wastewater. So that this process depends on the amount of water. So maybe 2 to 3 hours, 4 hours, something like that in these tanks. So constantly mixing the air and the wastewater in this tank, and then let bacteria work on those organic matter which are coming from the primary site. After that, the water moves to the next step, which is called secondary clarifier, because this is called secondary treatment. This is called secondary clarifier. And again, we let the water settle down here, all the solids drop on the bottom, and the water is on the top is very clear now. And these solids are again called secondary sludge. So we collect primary sludge coming from one side, secondary sludge coming from other side, and then all the sludge goes to sludge treatment site. And this water now, the much cleaner water, which has very few solids, suspended solids, but most of the water still has a lot of organic matter. They still have some nutrients in that. That goes to the next step. And then after that, we remove all the bacteria with disinfectant. And then we try to kill all the bacteria and viruses before the water is discharged to the surface water or river or lake or wherever it goes. So this process is extremely important part of the whole treatment system, because without this disinfection process, we will contaminate everything what we where the water goes. And in generally, those resources, the water where the water is going, they are drinking water resource. They may be lakes, like Lake Titicaca, or other lakes, or the rivers. So if you don't disinfect, then we will contaminate or pollute all the rivers and the surface water, and that can be really dangerous to the people's health. So this is one of the most important part of the whole treatment system. Okay, so the idea of the treatment disinfection is, again, I'm just trying to say, is to kill all the bacteria or inactivate. Now, there are a number of methods we use. The most common method is the chlorine. So we add chlorine in the system. This is the chlorine gas or liquid chlorine, we add that. Or the second way is to kill those bacteria or viruses is ultraviolet light or UV light. And this is the new method, which is getting very popular in US. This is called peracetic acid or PAA. This is a very new method. So I have been working on this method for the last 7-8 years. And now several clients I have helped to start this new method, which is very effective, very effective. And there are a lot of benefits of that. So I have been actually working on this method to get rid of chlorine. We want to remove the chlorine from the treatment, disinfection treatment, because of the problems, and want to introduce peracetic acid or PA for the new disinfection system. Okay, so now for the conventional method, like chlorine and ultraviolet, there are certain problems here. So one of the problems what we have is the chlorine generally does not kill every bacteria, or they don't kill or destroy viruses or protozoans, small protozoans. They are very, or you need very high dose of these chlorine disinfectants. Because of that, what happens, you have very high amount of chlorine, then it creates chlorine byproducts in the water, and you cannot destroy those water byproducts, and then they become part of your drinking water source, and becomes very expensive to remove those chlorine byproducts from the drinking water when you are processing that water and try to remove those things. So United States Environmental Protection Agency, or EPA, is trying to remove chlorine from the disinfection of wastewater because of this reason, because all the byproducts produced by chlorine, and some of the chlorine byproducts are very toxic. They also have some carcinogenic compounds produced, so chlorine is not very healthy. The problem is UV. The UV is extremely good, very effective, but there are 2-3 problems with the UV. That is very expensive because it uses a lot of energy. And then the second problem with UV is when you have high solid content in the water, UV does not work because UV rays are blocked by the floating particles, and then UV is not very effective. And also, if there is a color in the water, for example, some industries, they work on the color. If there is any kind of color, that can block the UV intensity. So UV has problems because of the water quality, and chlorine has a problem because of production of a lot of byproducts. So that's where we are actually talking about PA, or chlorine, PA, to get rid of all those things which we cannot remove by chlorine or UV. So let's talk about the disinfection part and where the future of disinfection is going. So now, as I mentioned, peracetic acid is my choice for the disinfection. And so I'm trying to, okay, so now what peracetic acid does is it produces a lot of advanced oxidative process method, produce hydroxyl radicals, which is the reason it is more effective than chlorine or UV. But what I have done in the last 5 years or so, combining peracetic acid with UV to create even more effective system, because UV also produces hydroxyl radical and peracetic acid does the same thing. So when you combine these two systems together, then you actually make an extremely potent and effective system. So that's where I'm going to talk a little bit more about the future. We recently changed one of the treatment plants in Cincinnati to adopt this system where we are adding peracetic acid with UV, and it has been very successful pilot study, and now we are switching that plant to the new system. Okay, so this is also called, I call double disinfection because we are using chlorine with UV. I also tried chlorine with chlorine and UV, and also UV and ozone. So they are double disinfection, but most effective is the peracetic acid with UV. So, and I have also tried peracetic acid with chlorine as well, but I don't like adding chlorine, as I told you the reason. So peracetic acid, which does not produce any byproducts, and UV has no byproduct. So this combination is the best going forward. And the second area, which is not being used by the treatment plants, that is electrochemical method. So that I think the future is more on the electrochemical side, especially for the smaller plants. And I will talk a little bit more about that in a few slides. Okay, so in the dual disinfection, when we are combining two different kind of treatments, like peracetic acid, which is a chemical treatment, and UV, which is a physical treatment. So when you combine those two together, so what we are doing, we are using very low dose. So we are not using the full strength, we are using just fraction of the strength of both treatment sites, because we are producing a synergistic effect of combining these two together. So that reduces the cost and increases the potency of the treatment. So dual disinfection has been extremely effective because of the synergistic effect of these two systems. So let me talk a little bit about the electrochemical, which is the most effective system I have found. I'm working at two plants, two places, one in Hawaii and one in one of the states in the United States. We are trying to use this electrochemical method and get rid of all the chemical or UV method, because this method I found is more effective and highly effective. Okay, so in this method, what happens? Chemical oxidants are generated in situ. It means at the location. So you are not adding any chemical in the treatment disinfection. You are producing chemical on the site by using electrodes. And so various types of electrodes are used for these chemicals, electrochemical treatment. And depending, that selection of electrodes depend on the type of treatment we are using. So if you are, for example, using, try to treat a waste coming from metal industry, you will use a certain type of electrodes. But if you are trying to treat a waste coming from a color factory where there's a lot of color in the water, then you will use a totally different set of electrodes. So you can actually customize the treatment, electrode treatment, depending on the water quality or where the need is. So that is the flexibility this system provides for the treatment. And this treatment we have found the most effective destroying the chemical pollutants, especially chemical pollutants which we cannot destroyed by either chlorine or UV. Chemical pollutants are not affected by those treatments, but chemicals are destroyed by this treatment, electrochemical treatment. So here again, we are using producing hydroxyl radical, and also we are using producing chlorine radicals by using these electrodes. So let me go to okay. Here, just kind of basic system how it works. So there are two electrodes, anode and cathode, and there's a power going from, they're connected, and this is filled the water. This can be small chamber or it can be large tank. This is a very basic system. So anions are produced here and cations are produced at cathode. And so on this anode, oxidation process happens. On the cathode side, the reduction process happens. So that's how. So electrodes are transported from anode to cathode. And so on this side, all the chemicals will be reduced, and on this side, chemicals will be oxidized. So this is another slide just to demonstrate how it works. So for example, if you are having some chemicals, drugs or pesticides or any other things in the wastewater, so by using this method on anode side, you are producing hydroxyl radicals and also chlorine radicals, and then you are oxidizing process here happening on this side, on the anode side. And on the cathode side, you are actually reducing all the chemicals. So you actually have two different kind of treatment going in simultaneously: oxidation, and reduction. And that breaks down all the long chain chemicals into complete carbon dioxide final product. Or if you have nutrients in the chemical, for example, nitrates or phosphates, those can be reduced to nitrates, can be reduced to complete nitrogen gas. So you can totally destroy everything, and you can get very clean with effluent after that. So this is the system which we are using at one of the treatment plants. So water goes from here, and electrodes are in this chamber. So water goes from here and then treated through anode and cathode here, right in this chamber, and comes out. So when it comes out, then it's already treated. So because the small time water goes in this chamber is not enough to destroy all the chemicals or treat all the waste. So we have number of these reactors in series. So you can have 10, 20, 50, depending on the need of your water treatment. So this can be changed or modified or customized. So in the series, so water goes from here, it comes out, and goes to the next reactor, and so on. So keep going from reactor to another reactor, and in the end, you can test the water, and we will see that almost all the bacteria, all the viruses, all the chemicals are destroyed. So this is very effective in the sense because you can plan how many reactors you need, and if one reactor goes bad, you can actually replace just the electrode on one reactor, so all the reactors are still working. So it is very effective in the sense that you do not have to replace the whole system. You can just replace one reactor at a time. So this is because the water is not what is a resource. It's we cannot lose the water. We have only limited water on this earth, so we need to use that water very carefully. So all the water which we don't use, we waste, and then the purpose of this area is that we need to recover as much as water we can, and the nutrients is the second part which we need to reclaim, and the rare earth metals. So these are the three things which we can get back from the wastewater. So by cleaning that water by electrochemical or other methods, we can get water back, which can be used for fertilizer, for farming, or it can be used for reclaiming and reprocess for drinking. Namibia, where I went for Fulbright, that's where they use the water. For about 35% water comes from the wastewater treatment plant. So they clean that water and reuse for drinking, because that country had absolutely no rain, zero rain, and there's no water in that country. So they use for drinking. So these kind of reactors, we can reclaim all the water. And the nutrients, which the number of techniques, we can get the nutrients back, especially the phosphorus, which is coming from the mines, and we have limited amount phosphorus in the earth, so we need to reclaim that phosphorus. These treatment systems can be used to get phosphorus back, and also rare earth metals. We did one big study in the US, about 20 different plants. We participated in that, and we checked the rare earth elements coming from different treatment plants, and we found that those plants, those are the rare earth elements, can be recovered from the sludge. And that is another resource. We are actually working on that. So don't think that wastewater is waste. It's not wastewater. It's a resource water, actually. So we should use that, think about resource for getting water, nutrient, and rare earth metal from this water. And with this, I want to thank every one of you for your attention, and I would be happy to answer any questions.
Thank you so much, Ashal, for your great presentation. This was such a valuable information for all the participants. Please stay with us, because we will be having a time for questions at the end of the event. So thank you again so much for this great presentation and all the information you have shared with us. And now we're ready to welcome Selena Rakbok. She has completed a PhD degree in chemical engineering at the University of Sao Paulo in Brazil in 2014 in environmental technologies. Meanwhile, she has also participated in a doctorate fellowship at the University of Texas at Arlington in Texas, USA. And also between 2014 and 2016, she has worked as a postdoctoral researcher at University of Sao Paulo and also at Federal University of Rio Grande in environmental sciences. She has worked as a professor at the Dickinson State University and also Dallas College, and currently she's working at the Collin College in Texas in United States, and also she will be soon joining the Tarleton State University in USA as well. Her research interest lies in the field of water and soil treatment techniques, with a focus on treatment of emerging pollutants by advanced oxidation processes. So now we are ready to welcome Selena, and please join us in this event with your presentation. Thank you again for your time and for sharing all your knowledge with us. So thank you and welcome, Selena. Let's begin with you.
Thank you. Can you see my presentation?
Yes, we can see it.
Okay, thank you. So thank you for the introduction. It was great introduction. So thank you for the invite. So I'm Selena Rakbok. I'm working in Collin College. And the title of my presentation is Degradation of Emerging Pollutants by Persulfate and Hydrogen Peroxide Activated by Aero-modified Diatomite. So the main objectives of the presentation will be to discuss these two papers that I am one of the authors. So the first paper is about the treatment of a hormone 17-alpha-ethinylestradiol in water. We use persulfate activated by aero-modified diatomite. This research was carried out in Brazil. And the second paper, the second one here, is the degradation of PFOA by hydrogen peroxide and persulfate activated by aero-modified diatomite. This one here was the experiment were carried in University of Texas at Arlington. Okay, so both they are emerging pollutants. When we work with emerging pollutants here, the emerging pollutants, they have a continuous entrance, continue entering the environment They are persistent chemicals, and there are more than 40,000 emerging pollutants. They can be pharmaceuticals, synthetic hormones, homemade products. And one of the biggest challenge of the research to work with this work of emerging pollutants, because usually they do not have intervention values, neither regulate analytical methods. So one of the pollutants is the PFOA that they worked with. And as there are some research that show that about more than 200 million Americans may have consumed water contaminated with PFOA. And that PFOA can relate with the high risk of higher cholesterol, thyroid disease, some types of cancers. Okay, and the second pollutant about another article is this hormone 17-alpha ethinyl estradiol that may affect the reproduction and development of the fishes. So the conventional wastewater treatment may not be effective to treat this pollutant. So what to do? What we can do to help to solve this problem? So one of the alternatives is to use an advanced oxidation process, AOP. And the focus of the AOP is the generation of highly reactive oxidizing species, such as sulfate radicals or hydroxyl radicals. And these three oxidants here can be used for this technique, advanced oxidation process, like persulfate or hydrogen peroxide or ozone. But these oxidants, the oxidant by itself, they will not generate radicals, because what we're going to be treating the pollutants will be the radicals. The radicals that are reactive species that we wanted to react, right? So let me give an example here, talking about the persulfate. Some persulfate activation methods. So yes, you have here 4 different types of activation. For example, heat above 35 degrees Celsius, photochemistry, alkaline, metal activation. And you see here that first you have the ion, the persulfate ion, right? And you need the activation to convert the ion to a radical. For example, here the one that's blue here are the sulfate radicals. Let's look for the metal activation here, the last one. You have the sulfate, the persulfate ion will activate with a metal, right? And you produce the sulfate radical. And the sulfate radical that will gonna break degrade the pollutants. In this condition here, so the metal needs to be in very low pH. So yes, the traditional activation by metal, one of the main disadvantages is they needed to be in very low pH. And you know that in very low pH can negatively affect the environment, right? It can change the conditions, the properties of the soil and the water. So the purpose of this research, both papers, is the same purpose. The use of new activation method. And what's the new activation method? It's a method that instead to use it in a homogeneous, a solution with iron in a homogeneous system, we're gonna use it in a heterogeneous materials. This heterogeneous materials is composed by a low-cost support, that's the diatomite. We have a picture below here of the diatomite, on which a combination of iron 2 and iron 3 ions in the form of iron oxides are impregnated on the surface of the diatomite. Okay, and the main advantage here is that it's efficient in a wide range of pH. This is the main purpose of this technique. And there is no need to lower the pH to work with this modifying diatomite, iron modifying diatomite. And the purpose here is going to be environmental friendly and a low cost material. Okay, so just explain a little bit more. So the material that we're developing is support the atomite, right? And you precipitate ions on the sulfate. So iron impregnated here on the surface. So then you have it, you add the oxidants like hydrogen peroxide or persulfate, you add on the catalyst the material, and then the ions became what? Radicals. So the radicals we can produce, depends on the condition of the reactant of the system. You can produce reducing species like such as superoxide, or oxidizing species, sulfate radical or hydroxyl radicals. So you work in lab scale using batch scale here. For both papers, you use the same methodology. Use it LMI contaminated water, and you add the modified atomite in the oxidant and water, and you took a liquid of the sample, and each time, every time, like every 30 minutes, for example, using this extraction here, SPE, that's solid phase extraction, and we have 40 steps here for this extraction. And after the extraction was analyzed in the HPLC. So okay, we have two pollutants, PFOA. We worked with PFOA in one paper, and another paper was the hormones, right? EE2, 17 alpha ethinyl estradiol. So characterization results. I'm just showing here just the main results. For example, for the iron, the X-ray fluorescence total iron showed that when it was just the raw atomite, the total iron was 4%. But when you did the modification of the iron, changed from 4% to 21%. That is very good. This is the purpose, because the post was impregnated iron on the surface of the atomite, and also to reuse the material. Okay, let's begin with this paper here. A comparative study of persulfate activation by iron modified diatomite and traditional process for the treatment of 17 alpha ethinyl estradiol in water. This research the experiment were done in Federal University of Rio Grande do Norte in Brazil. Okay, so you can see here, first experiment, this you did many preliminary experiments. And let me talk here about the experimental design A. Experimental design A, you use traditional activation methods. Why did it call traditional here? Because I did not use modified atomite in the experimental design A. We did not use it, right? This one experiment is carried out by a student. And what happened here in the experimental design, talking about statistics here, you have the three variables: persulfate concentration, temperature, and pH. The pH was ranging from 3, 7, and 11. And the best results using these experimental conditions here was the gradation of the hormone was 90%, right? He was just the traditional activation methods. Why? Because on the previous slide, we showed that what heat is one activation method for persulfate, right? And also alkaline pH. So he was studying, try to compare which one is gonna be better. We're talking about the traditional methods. So 90% were obtained when you used 20 grams per liter of persulfate, 45 degrees Celsius, and pH 3. So it's a good result, but unfortunately it was still not good environmental conditions, right? The pH was too low here. And also the concentration of persulfate was too high to work with. Okay, let's talk about the worst results. Let's talk about what's good. Let's try to understand why it was not good here. So you can see here what's a circle in yellow here. For example, the 14% degradation. So just see one thing. This result was obtained was in 90 minutes degradation, just 1 hour and a half. And the 14% that was very low degradation was obtained using 20 grams per liter of sodium persulfate, 45 degrees Celsius, and pH 11. And you can ask, but why when you did the two techniques together was not efficient? So, because maybe here happen another more reactions here that instead to be producing the oxidizing radicals, maybe produce another species, and maybe was scavenge like the sulfate radicals, and probably produce another radicals, another reactions that was not effective for to produce the sulfate radicals. Okay, this is the surface here for the experiment that I showed the table before, right? The best results, 90% results using traditional methods. You compare alkaline with in heat. And the experimental design B, you use the modify the atomizer here, a new activation method. And for this experiment, you just use two variables, persulfate concentration and modify the atomizer in grams here. And the best results was obtained here on the run number 3, right? That was obtained 98% degradation. Let me show the surface here. 90% removal, use modified atomizer 1.5 grams, and persulfate 10 grams per liter. So, and you do not need to lower the pH. The pH was as it was naturally. You did not need to do anything with the pH was okay. And here, the surface was obtained using Statistica 13, the software Statistica 13. And what you did, so this software gives us an equation, okay? In this equation, you plug the equation from the software in another software called MATLAB algorithm F-minicom function to get the optimization of the experience. Like what is the optimization? So the outcome point, according to the MATLAB, gives us that was 1.7 grams of modified atomizer and 11 grams per liter of sodium sulfate. You're going to be the optimal point. So you know what you did? Okay, let's try to do this exactly conditions that the software said us to use, right? So you did it. And you also try to do a test to reuse it to see, okay, let's see if this modified atomizer can be reused. And you did it. The test is here. And like the first reuse was 94% removal, and the second was 93% removal. That means it's very, very good, like that you can reuse the modified atomizer, right? Without basically not lose the efficiency, because 1% difference may be just a experimental error. So the conclusions about this paper is that these hormones can be treated by oxidizer radicals, such as sulfate and hydroxyl radicals. This modified atomizer treatment show higher efficiency than traditional, right? That we use modified atomizer to achieve 90% removal of the pollutant of the hormone here. And the catalyst reuse test show degradation, similar results of the test used for the first time and the second time show similar results. So for the second paper, just to show a few slides here just to compare. So this one was using degradation of PFOA by hydrogen peroxide and persulfate activated by iron modified atomizer was These experiments here were done in the University of Texas at Arlington, United States. So let's talk about the results here. So the POF, this experiment, you did it in 6 hours of the reaction, right? And the hormone you did in just 92 minutes. Okay, so you begin to do this experiment here, and you can see here the first graphic here. It does not seem so good, right? So what was the conditions here? Sulfate plus modified atomite was still not efficient. Okay, so let's try to change the pH here. So we did a second experiment, second trials, change the pH here, 3, 9, and 12. And you can see that when we begin to change it to 12, the pH 12, you can see me begin to improve the removal, right? Here. And okay, let's try to be, so let me go back here. What's the difference between pH 3, like you can see that the last one, the pH 12, you are doing a combination of 2 techniques, modified atomite and pH and alkaline media, that means iron and alkaline, right? So, and you can say, but PFOA is showing better results when you do 2 techniques together, activation methods together, right? And the hormone was not. Said yes. Why? Because the hormone was effective by oxidation, right? And here we suggest the PFOA. What's happening here? We are doing conditions to generate reducing radicals, such as superoxide radical. So, for example, here, this graph here, the figure 6, you can see that when the hydrogen peroxide with sodium sulfate together, you also can get a removal right here. So depending on the conditions, yes, you can generate superoxide instead of hydroxyl radicals here. Depends also on the condition, the concentration of the hydrogen peroxide, the pH, and also fits in the system here. And the second one, the second graph here, figure number 7. So you can see that hydrogen peroxide and iron, this one here using homogeneous system without modified atomite, was still kind of similar, right, to the modified atomite. The point here was to show that it was better with modified atomite, but show that probably in this condition, the point here was because of generated superoxide. Reducing radicals to maybe want to be degrading the PFOA. So what you can understand here, degradation of PFOA use modified atomite with hydrogen peroxide and sulfate may be effective only on according to the conditions applied here, may be effective only on favorable conditions to produce superoxide radicals. And the best results is just 86% removal in 6 hours using high concentration hydrogen peroxide and modified atomite. So it's still not great results. You need still to work better for this condition. So further researches here, if you're gonna continue work with the research, you need also to improve the conditions and to analyze the sub-products. Because for this experiment here, we're not able to analyze the sub-products. Actually, because my time there doing fellowship at UTL was finishing, so not able to analyze more about the sub-products. So, but what to do with this technique? What's the proposal here? So, application proposal is to do after the traditional wastewater treatment steps. You add a barrier filled with the modified atomite, and you add the oxidants here to produce the radical species to do the pollutant degradation. Okay, this is the application suggestion here. Gracias.
Thank you very much, Selena, for such a great presentation and also for sharing with us all your knowledge and expertise. So now that we are approaching the end of this event, I think we are ready to some questions. So for all the people in the event, I have to remind you that you can put your questions, type them on the question panel if you want to make some questions for our speakers. So let's begin with question number 1 for Dr. Kostel Bumbak. David Luna is asking, would you recommend biological wastewater treatment over chemical treatment? And also, if you could please share with us the main difficulties and challenges you encountered when implementing the Inocua system.
Yes, thank you very much for the question. I have already answered in private, or I think in the chat box. However, I will say it out loud as depending on the wastewater treatment, or on the wastewater quality, whether it's municipal or industrial, you can choose the treatment process or the treatment train needed for safely discharge or reuse the treated effluent. So usually for municipal wastewaters, biological processes are advised or preferred. And at some points, physical or chemical treatment steps need to be added as pre-treatment for some industrial wastewaters, or in order to reach the influent quality, which can be directed towards a biological step, or as post-treatment step, usually in municipal wastewater treatment for phosphorus chemical precipitation. So chemical treatment can be part of a treatment train, including biological treatment, depending on the wastewater constituents and treatment target. Regarding the second part of the questions on the Inocua project and challenges, let's say we can begin with the loss of 2 of key partners, which of the project. One was an industrial partner that was supposed to build the reactors, and the other one was a technology provider. So key partners that had to go away from the project during the project. And we were lucky to have on the team enough skilled partners that were able to take the responsibilities on the way and lead the project towards success. Another challenge was to source and to find the biological material needed in some countries. For example, earthworms or daphnias were hard to get in Tanzania, or even in Romania, we had trouble finding daphnias, as it's not a common commodity, so to say. So we had to breed the daphnias in the lab, or we brought the earthworms, we bought them from a composting farm. Another challenge was to homogenize sampling and analysis protocol so that we can compare the results from all demonstration sites from 11 countries. And one more challenge that was rather unexpected was the extreme sensibility of daphnias towards the environmental conditions, especially in low temperatures during the Romanian or Irish winters, which were below freezing point, or high temperatures in India and Tanzania. I hope this answers the question.
Yes, I think that was very complete. Thank you very much, Kostel, for your participation. And now let's go with question number 2 for Dr. Ashal. It says, in Peru, there are very poor areas where the government has not yet implemented water treatment plants. In that sense, what technology or method do you recommend to treat wastewater in rural areas where houses are frequently isolated and disconnected?
Okay, so yeah, you're right. Even actually in Puno, which is a fairly big-sized city, more than 100,000 people live there. There's no treatment plant there in Puno. So all the wastewater coming from the homes and the rain, everything, that goes to they collect it and then process through a series of oxidation tanks and then goes straight in the lake Titicaca. That's what my research project was, to investigate the effect of that wastewater. So yeah, it's not only rural areas, but it's even big towns like Juliaca and Puno, they don't have treatment plants. So that is very unfortunate. Puno is going to build a plant. That is a good news. It might take 5-6 years. But coming back to the small communities, building a treatment plant is a very expensive process. It's not easy to build. It requires a lot of money because you have to first collect the water from each home. So each house has to be connected to the treatment plant. So you have to build the collection system, underground pipes, and then treatment plant itself is very expensive. So it requires a lot of money. So I don't think that it will work for a small community. In that situation, I think you need decentralized treatment system for each house or each small neighborhood. You can have a small neighborhood with 10, 20 homes, and then you can have a small system right for the community. So that is the one option you have. Now, for that, there are a number of technologies available in the industry, so that can be used. But I think wastewater treatment is not an option for small communities. So I think the only way they can do is individual house, they have their own treatment system, and then they treat their own waste. And I think we already had one presentation. One speaker spoke about the small treatment system. Those are available, and there are so many other treatment systems available in the market. And we are building one treatment system. Actually, I'm building in Bangladesh for a school where there are about 1,500 children. We are building a treatment system for them as well. So there are a number of options available for small communities.
Okay, thank you very much, Ashel, for your answer. And now let's go to the final question, and it goes to Selena. It says, what types of tests do you recommend when experimenting with new forms of wastewater treatment, and what parameters should we consider? Your microphone was off?
Yes, I am back here. So for the treatments, first we need to study the chemical, right? Which pollutant, to know what are going to be the best conditions, because here I showed two different chemicals. One was using reducing radicals, and another was using oxidizing radicals. So before you choose your conditions, you needed to study your chemical, your pollutants, to see what are going to be the approach. So in my presentation, the presentation about the oxidation process and reduction process, like advanced oxidation process and advanced reduction process. So before you choose your conditions, understand it, study your chemical, the chemical that you are working with.
Great, thank you so much, Selena, and thank you very much to all of you who joined us today to discuss about such a relevant topic, sustainable water and wastewater management. Let's not forget that in terms of water, just like every single drop counts, every single effort, even big or small, also counts. So before finishing, we remind you that today is the great celebration of Universitas 2022, which will start at 6 p.m. in the gardens of the San Lázaro campus. On behalf of the Department of Industrial and Environmental Engineering and the San Pablo Catholic University, we thank you all for your kind assistance at the International Environmental Conversation about technological innovation and strategies in the availability and sustainable management of water and sanitation in terms of the SDG 6. Until next time, and remember, go out there and be the change that you want to see in the world. This session is officially finished. Thank you so much all for your assistance. Have a good day.
Thank you very much.
Thank you. Have a nice day.
Bye-bye.
Thank you all.
Tenemos una historia que habla de nuestro corazón, la fuerza de nuestros sueños, el orgullo de nuestras raíces.
Hoy nos toca hacer y seguir camino, levantar el país que imaginamos, tejiendo sueños y esperanzas.
Historias, orgullo, pasión, memoria, trascendencia, prendidos en el alma.
Universitas, un corazón que abraza su historia y su futuro.
Somos grandes historias, orgullo, pasión, memoria, trascendencia, prendidos en el alma.
Universitas, un corazón que abraza su historia y su futuro.
Somos